This video goes along with chapter 18 of this book, and in this video I'm going to do the same calculation as I did in the video on chapter 16, but now I'm going to do it with solid elements instead of beam elements. And I've also done it in shell elements, and I'm going to compare all three of the results to the analytical results as well. Here you see the advantages of beam elements and solid elements. So beams are faster and they can show a moment graph. Solids are slower and they can show a moment graph but have more possibilities, because with beam elements you can only calculate beams logically. Shell elements give a little bit more possibilities, like calculating thin-walled structures like cupboards, etc. And solids have the most possibilities in calculating construction. So you should be able to calculate everything in solids, but it doesn't show a moment graph and it's slower than beams and shells because it needs more elements. So I'm gonna show that in this video. Here I have a table of all the calculations. You see here the analytical results, which I also show in chapter 16, so check that video if you're interested in that, of the stress and the deflection. I've also got the results in beams and shells, and the explanation why there is a difference between the analytical results and the beam and shell results are written over here. So the simulation takes the shear into account, which your normal analytical analysis doesn't do. And the shell elements are also an approximation of the final result, so that's why it's got a little bit higher stress and deflection value, and the reason for that is written over here. So now I'm gonna do the same calculation of a beam in solids. So I'm gonna switch over to SolidWorks and create a new part, and then it's most convenient to draw it as a weldment and then analyze it. So I'll take a beam of 1 meter long, like I've done in the previous videos as well. Then I'm going to use a weldment and take the structural member over this line. It's the beam is pre-selected over here already, HE100A, and if you don't see it, then you should download more weldment profiles. You can do that over here in this task pane. If you can't find it, maybe it's good to check and search for a video on that. But don't go and draw your own weldment profiles, because it's a waste of time, and the downloadable weldments are better in quality. So I'm going to rotate it right now for 90 degrees like that to get the beam in the same positions as the previous calculations. Then create a new simulation study, and now it sees it as a beam element. If you don't want that, and in this case I don't want that, I have to treat it as solid with a right mouse button. So now it's a solid, and SolidWorks will mesh it as a solid, and then I'm going to fix this geometry. I'm going to fix this whole line over here, and it's still able to rotate, but it's not able to move anymore. And in SolidWorks you cannot suppress the rotation of a solid element apart from fixing a whole surface like this. But I don't want to do that over here. I want to fix this line here as well with reference geometry. So I'm going to use the use reference geometry option. Select, for example, this line. I don't want to move this line in the direction of the green arrows. So now I've set up the model as with the other two previous performed calculations, and I'll put a force on the top of this beam of 100,000 Newton, which is the same as in the previous two analyses, because it was 100 Newton per millimeter as a distributed load, and it's the same as 100,000 Newton divided over a meter. So now I should get the same results as in the previous two calculations, and I should be able to fill out this table that you see over here. So I'm gonna see what SolidWorks returns as results. Run the study. I get the meso stress, and I don't want to see that right now. I want to show the stress plot in the x direction. You see it corresponds to this coordinate system over here, and I get a value of 240 and minus 171. The high value is the stress concentration over here. So if I want to check the results over here, then I should probe this plot over here, and I can see a value of 175 Newton per square millimeter, which is close to the previous two values. It's only 3 Newton per square millimeter difference, and the finer your mesh would be, the closer the results would also be to your beam and shell analysis. And I can also look at the displacement. I see displacement of 2.26 millimeters, and it's also quite close to the previously analyzed values, and also this value will get closer to the final results of the beam element if you mesh your solid elements finer. So now I've done all the analysis, and I hope this gives some clarity in when to choose which kind of elements, and also how some differences in result of an analytical analysis are different compared to a FEM analysis. So thanks for watching.